Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, what have you learnt from octopuses? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week I'm finding out about how researchers are taking inspiration from nature to design soft, flexible robots for applications in healthcare and rehabilitation. But first, I'd like to remind you to subscribe to Robot Talk through your favourite podcast provider to make sure you're the first to hear the latest episodes. Another way to find out about new episodes is the email newsletter, which you can sign up to by going to robottalk.org. So, without further ado, let's get on with this week's interview. I recently had a fascinating discussion with Maria Elena Giannaccini from the University of Aberdeen about soft and bioinspired robotics for healthcare and beyond. This week, I'm speaking to Maria Elena Giannaccini, a lecturer in robotics at the University of Aberdeen, researching soft and bioinspired robotics for healthcare and beyond. Hi Elena, welcome to Robot Talk.
Hello, Claire. It's very good to be here. Thank you for inviting me.
To get us started, can you tell me a bit about your research on soft robotics?
Yeah, it's very much a passion. It's a job, but also a passion. I started working in soft robotics during my MSc thesis. I was lucky enough to work with Professor Lasky in Scuola Superiore Sant'Anna in Italy for my dissertation, and that was within the OCTOPUS project.
Okay.
Which was a really interesting project where we were working on making a robot out of soft materials inspired by an octopus.
Cool.
Yeah, very, very. We actually had a tank with an actual octopus in the lab. So
nice.
Was
wow.
Cooler than the usual lab. And then the lab was right by the beach. And we had a chance to, kind of make the robot. So I was working with an arm that was mimicking the reaching movement that octopi do in order to grasp their food. And so we had a chance to kind of reproduce this movement in a tank. Of course, ours was made of silica, but see it right next to the actual octopus.
Yeah. Did the octopus react to the robot? What did it think of it?
I'm not sure, but we actually, some of us were feeding the octopus. They had more of an interaction with it. I was just observing it and finding it really incredible how it moves.
Yeah.
And how it grasps onto things and really shapes itself around a jar or
Yeah, it's amazing.
Yes, and that really also sparked my interest not just for soft robotics but for bioinspiration as well, because when you can see the amazing abilities that these animals have, then you do think, yes, this is a good starting point for a new work. And then when you learn about bioinspiration, you think about, because they always tell you, you create a robot, and the robot can be inspired by an animal, and then the robot can do some of the things that these animals can do and solve problems that are otherwise difficult to solve in our unstructured world. For example, molding its shape to an object, which is hard for robots to do. That's why grasping is still such a challenge for robotics. But also there's kind of the other part of the bioinspiration paradigm, that we can create a robot that can be used to test a biological theory. And in that project, we were working with biologists. We got to talk to them, and they were telling us, okay, so that's what we think. The hypothesis was that it was a stiffening wave that was actually making this grasping movement happen in the octopus arm. And we tested that with a robot arm that was specifically made to test this theory. So it was, the two worlds, the biology and robotics, really came together in that project. Yeah. And that's what inspired me to keep working in this area.
Amazing. So was the theory correct about how the octopus arm worked?
We saw that it was a very possible hypothesis. The difference that we had was that, the materials are really different. When you look at, you're working with silicone wire, they have muscle.
Yeah.
The structure is completely made of muscle. And we think that the differences that we could find were, quite related also to the material.
Okay.
But, it was really interesting to see how with those materials you could actually comply the shape of the robot to objects we were able to grasp. Let's say a bottle, for example. It was quite simple to do that.
Yeah.
So it was really interesting work.
Yeah, I love it when it kind of comes full circle and the biology inspires the robotics and then the robotics informs the biology. Really cool.
Exactly.
So fast forward to today, what projects are you working on now?
So I work still with soft robotics. My main research work is about a wearable for rehabilitation for stroke survivors. So what we have nowadays is that people who get stroke, they don't have access to enough rehabilitation. So there are new guidelines that say that theoretically one should rehabilitate their upper limb about 3 hours per day, 5 days a week.
Right.
And that is a huge amount.
Yeah.
But, the idea is you should try to start your rehabilitation as soon as possible after the stroke and have a high volume.
And that would be with a physiotherapist, I guess.
Yeah, so as of now, it has to be with a physiotherapist. And of course, even just the availability, it's not possible. That's why we're looking into building something that stroke survivors can use and can be set up together with a physiotherapist. The initial exercises would be with the physiotherapist, but then something that hopefully one day they'll be able to take home to do, to try to get to this amount of ideal rehabilitation. And we see that luckily a lot of work has been done for lower limbs.
Okay.
And we see there are even commercial products for the lower limb where that wearables that help them walk or help with their rehabilitation, but not as much as happened overall for the upper limb. There are great examples of work out there. Work done by Harvard, for example, but of course the field really needs a lot of work coming from different sides in order to to try and make a difference in these people's lives, because quite a few people have issues with their upper limb after this. And also it's not just for stroke, but these kind of wearables can also be used in other conditions where the mobility of the upper limb has been deteriorated. So now we've made this wearable device, and we've conducted experiments to characterize it. And also I'm very proud of the fact that we've worked together with other researchers in a project under the umbrella of Emergence Network Plus, which is EPSSE funded project. And we had this small project where we've shown this wearable to the residents of a care home called Blackwood Homes, the residents and the staff. and we've asked them, what do you think of it? And we asked them to put it on, to try it, and tell us what they think. And that has been an incredible experience from the point of view of learning what people want. Because so many times as researchers, we're a bit kind of, stuck in our labs.
Yeah.
And we have, a certain target that we want to reach. We want to, make a platform, a robot that has X, Y, Z characteristics. And that's what, it's really important to us. But maybe when, we cross the threshold, we, go outside the lab, we show it to people who we think might use that, then we see that some of the aspects of it might not be what they want.
Yeah.
So it was really important to do that. So we got to do that with potential end users and the PhD students I work with. We also showed that to clinicians and we got their feedback as well. So the idea is that we're going to keep working on kind of new versions of the wearable system and try to make it as usable and also as easy to accept as possible. And that kind of brings me to another side of the work I've been doing. So I've been lucky enough to be able to collaborate with the School of Psychology we have here at the University of Aberdeen. And we've worked on human-robot interaction. And that to me is, really fits together, because if you're, making something that people have to wear on themselves, then that interaction is really important. Yeah. Because it's not just a robot, like a wheeled robot that you have in the room, where already, the interaction is really important. You want to really get the cues right in order to have acceptability. But when, the robot is mounted on yourself, is strapped on you, and you either you accept it, you want to work with it, or it's really not going to work.
Yeah.
Because for many years, I've worked in different labs. So as I was saying, Scuola Superiore Sant'Anna first back in Italy, and then for about 10 years at the Bristol Robotics laboratory, where I did my PhD thesis and then some postdoc work. And you would see all these people visiting and seeing these robots, and some were really interested, and some were a bit scared. Scared of these robots, and they were very, very happy to be interacting and look at that and think, okay, how can we, try to bridge this gap, because we're making these robots so that they will be helpful, useful in people's life, whether it's for rehabilitation or for other uses. But if people don't want to work around them, then everything becomes harder.
Yeah. Going back to the wearable device for stroke rehabilitation, can you kind of tell me a bit about how that works? Is it kind of creating resistance for certain exercises, or how does it work?
So as of now, it has a soft actuator that bends the elbow.
Okay.
And the soft actuator is basically some textile, but it's made so that it's airtight, and you push some air in and then it expands. It has some pockets, basically, that shape the way it expands.
Okay.
So we push this air in, the pockets expand, but in the work we've seen around, the actuator is usually kind of stuck to the arm. So it follows the arm, is along the arm, along the longitudinal axis of the arm. And that can sometimes restrict the movement. So what we've decided to do is to have what we call a decoupled actuator. So we have 2 points of contact, one in the forearm, one in the upper arm.
Okay.
And those are the 2 points where the actuator is attached to the arm. Okay. because the actuator is basically in parallel to the arm, that it doesn't restrict the motion. And in order to rehabilitate somebody, you really want this range of motion to be as large as possible, because you want the full movement. This is shown to be needed also looking at the activities of daily living, which are things that we do every day. We don't even think about it, luckily when we're healthy, like putting on clothes or brushing our teeth or feeding ourselves. But these are all the kind of things that people who need rehabilitation need to get back to be able to be doing.
Yeah.
And so we wanted to be able to, for this to happen, so we wanted movement to be able to be done as we would normally do it, hence this placement of the actuators in parallel to the arm. So we now have the actuator, and lately we've added IMUs to the soft actuators. So we're now able to control the position of the actuator, so we can tell the actuator, take this arm up to an angle of 50 degrees or 90 degrees.
Okay.
And what we're finding, that it's not surprising, but still interesting for that to be shown by experimental data, is that first of all, the movement of the actuator is very non-linear. So we know that soft actuators are non-linear, but this is shown even further. And that even though, we've tried with people of different build to bend their elbow, and we're able to bend it for different people at certain angles in a repeatable way. You'll need a different input for different people.
I was going to ask about this, yeah.
Yeah. Very much so. So we've had, different people try the wearable, because, as I said, we were trying to get it out there and get as much feedback as possible. And we've seen, completely different interaction. We call it physical human role interaction, depending on the person. And the good things about these kind of system is that differently from rigid wearables, you don't have to have an exact match between the point of bending of the actuator and the arm, which instead you absolutely need to get right for rigid ones. Because if there is a misalignment between the biological joint and the Revolut joint, because when a rigid one it's just a joint, a hinge joint. If there is a misalignment there, then that can hurt the person wearing it. So the beauty of these systems, that's why we could, many people try it, because there's an intrinsic safety in the fact that it's a continuum system, rather than something that it's that has to be built or it has to be really customized for the person.
Okay.
But then the flip side is that, anyone can wear it. But then when you try to control it, you see that, the same input really gives different, actuates the arm in different ways.
So for listeners who might not be familiar, could you explain what you mean by the soft actuator moving in a non-linear way?
Okay, so I was talking about a joint, a hinge joint. So the hinge joint is what you have in a door. So when you push a door close, the more you push, so the force in which you push is proportional to the angle at which the door closes, because it's rigid. So the pushing that you do, when you the door handle just transmits, because it's rigid, right to the hinge, and then you push. The more you push, the more the door closes. And if you were to kind of create a graph of door angle versus the force of which you push, you'd find a proportional correlation between the two.
Yeah.
The more you push, the more the angle closes. However, when you've got something that it's basically made of soft material, May that be silicone, or may that be, in our case, is textile and air. Anything that it's like that will not have this nice proportional relationship between your input, that for us is the pressurized air, how much pressurized air we've got in this bellow, which it could be 0.5 bar, 1 bar, 1.5, we can increase that. But that does not translate to it's always the same movement.
Okay.
So that is a first level of difficulty. And then there is another level, which is the fact that this system, which is already nonlinear, so we don't know exactly how it's going to bend, is attached to something, the wearer's arm, that it's itself compliant.
Yeah.
And has...
This is very complicated.
Yes, so the complexity builds up.
Yeah.
And also, we are, different people have different arms. So, people sometimes have more muscle, less muscle, or have different tones of muscle. Or if, of course, we talk about people who have a disability, or, their tone can be, again, different for stroke. You can have spasticity. So the complexity increases. But even just looking at, something that it's non-linear, input, output, and then put on top of something else that it's also non-linear, the complexity increases. So that's why we're looking into more complex ways to control this. For now, the control that we're doing is really straightforward, but we know that we have to build on that.
Mm-hmm. That's really interesting. Thank you for explaining that so clearly.
Thank you.
So we have an audience question from Lucas on Twitter. So Lucas says, I'd love to know more about the potential applications of soft robots in healthcare. Are they being designed to assist with surgeries or more for patient care?
So either. So thank you very much, Lucas, for the question, and I'll try my best to answer. So yes, the answer is either, and there is amazing work on both areas. So yes, soft robotics can be used for surgery. So there's areas that are very difficult to reach. So you want to try and use minimal invasive surgery as much as you can. What that means is that you want the tools to be as small and as flexible as possible. So that's why they've come up with these continuum systems, which are soft, but they are made instead of something that it's made of silicone, which is completely soft. Usually they're made out of modules.
Okay.
And then they have cables, and you only need 3 cables to steer something in 360 degrees. And of course, that helps going into areas which are hard to reach. Okay, so this is one of the possible applications, and actually was one of the applications that went into after the OCTOPUS project. There was a whole project called StiffFlop, where they were using these soft but also variable stiffness, which is something I've also worked with for surgery, because sometimes you want your robot to be soft and compliant. Let's say you're in a delicate area, especially if you're doing surgery, you want to be really delicate. Sometimes you want to be able to create some force on what's around you. And then in that case, you want the system to be stiff. So that's also another opportunity that it's also bioinspired, because the OCTOPUS can do this very their stiffness. And then for the second part of the question, yes, soft robotics can be used for patient care. In my case, we're working on wearable systems, but there are many different aspects of that. So, for example, I've worked in a project called RoboVox, which was really interesting, where we were looking at how to make an artificial larynx or laryngectomies. So sometimes because of different reasons, either trauma or because of cancer, the larynx, the voice box, needs to be removed.
Yeah.
And then it's not possible for people to speak the way we do. And that creates a lot of issues, of course, for communication and interpersonal interaction.
Yeah.
But also because that leaves a stoma, a hole, that means that there is a kind of a port for kind of potential for infections to happen. So it's it would be amazing if that could be removed. So we were looking at creating something with soft robotics, and the choice of soft robotics because because it's soft. And our body is, we have rigid skeletons, but also a lot of soft tissue. Then it's simple. It's much simpler to create an interface if what you're interfacing something soft, like our neck, with something that is also soft. And that was a project led by Professor Birch from UCL, and I was working with Professor Jonathan Roster at the University of Bristol, Andy Kahn, and others from UCL. I was working on the shape of this artificial larynx, but others were looking at the materials, because of course you don't want the materials to be such that it's rejected or encapsulated, so that it will never work. So it was a very, very interesting project as well.
Yeah, that's amazing. Eleanor, it's been fascinating chatting to you today. I've been talking to Maria Elena Giannaccini from the University of Aberdeen. Thanks, Eleanor.
Thank you. Thank you so much for having me.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @RobotTalkPod on social media to see a photo of the soft, wearable robot for upper limb rehabilitation that Eleanor and I talked about. Next week, I'll be speaking to Pratap Tokikar from the University of Maryland about robot swarms for environmental monitoring. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.